We'll start in 1 minute. Today we'll cover section 9.5 on linear differential equations. So first, a definition. A first-order linear differential equation can be written in the form dy dx plus p of x times y equals q of x. It's first order because the first derivative of y with respect to x appears in the equation. And it's referred to as linear because the function y to the first appears in the equation. Okay, so p of x and q of x are continuous functions on a given interval. Okay, if a first-order linear differential equation is not in the form above, then the first step before solving the equation is to write the equation so that it's in that form. Every first-order linear equation can be solved, and we follow the following steps. So step one, we get it into this form, dy dx, that's the derivative of y with respect to x, plus p of x times y equals q of x. So in step two, we multiply every term on both sides of the equation in step one by the integrating factor. So the integrating factor is found by raising the number e to the integral of p of x. And p of x is the function that we're multiplying by y in this equation. Okay, the effect of multiplying every term on both sides by this integrating factor is that after doing so, the left-hand side is the derivative of a product in which the product rule is defined. Okay, so we'll go through the steps. We'll multiply every term on both sides of this by e to the integral of p of x dx. So we get e to the integral of p of x dx times dy dx. And for the next term, I'm going to put p of x out front multiplied by e to the integral of p of x dx, and then times y. And on the right-hand side, q of x times e to the integral of p of x dx. The left-hand side is the result of applying the product rule for derivatives to a product. So we'll encapsulate the left-hand side. If we compute the derivative with respect to x of the product e to the integral of p of x dx times y, where y is a function of x, we get the expression that's above it. And on the right-hand side, we still have q of x times e to the integral of p of x dx. And let's, if this is confusing, let's see if we can make a little bit of sense out of it. So inside this set of parentheses, we have a product of two functions of x. Y is a function of x. And e to the integral of p of x dx is another function of x. And if we apply the product rule to take the derivative, well, up here we first take the derivative of y with respect to x. And then we add that to y times the derivative of e to the integral of p of x dx. So the integral of p of x dx is an antiderivative of p of x, and when we take the derivative of that antiderivative, we get p of x. So if this looks kind of weird, it's something that you've done before, just it hasn't been written in this form. Okay, in the next step, we can integrate both sides. So if we integrate the derivative of an expression with respect to x, then we just get the expression. So on the left-hand side, we get e to the integral of p of x dx times y. And on the right-hand side, the best we can do right now is just to write the integral of q of x times e to the integral of p of x dx, and then dx, and we'll put the constant of integration in. And the goal is to solve for y, so now we just divide everything on both sides by e to the integral of p of x dx. So we get y equals the right-hand side all divided by e to the integral of p of x dx. Okay, we'll look at a few examples of integrating first-order linear differential equations. Okay, here is our first example. Y prime is equivalent to dy dx if we're assuming that y is a function of x. So we'll get this into the form that we want. I'm going to replace y prime with dy dx. And then we'll add y to both sides. Okay, so this is in the form that we want. The form, I'll write that as dy dx plus p of x times y equals q of x. In this particular example, p of x is just the constant 1. So p of x is equal to 1 in this one. And so our integrating factor so in general, the integrating factor is e to the integral of p of x dx. But in this case, since p of x is just the constant 1, we get e to the integral of 1 times dx. which is just e to the x. Okay, with the integrating factor, we're going to multiply every term on both sides of this equation by the integrating factor e to the x. So we'll get e to the x times dy dx plus e to the x times y equals e to the x times x, but I'm going to write it as x times e to the x. On the left-hand side of this equation, this is the derivative of a product of two functions of x. So that means it's the derivative with respect to x of the product e to the x times y, where y is assumed to be a function of x. And then the right-hand side is x times e to the x. Now we integrate both sides. Well, when we integrate the derivative of a product of two functions of x, we just get that product of functions of x. So e to the x times y on the left-hand side, and on the right-hand side, we want to compute the antiderivative of x times e to the x dx. So we've done integrals like this before. If we use integration by parts, this turns out to be x times e to the x minus e to the x, and then plus a constant. So you can verify that this is the correct antiderivative. Okay, the goal is to solve for y, so now we just divide every term on both sides by e to the x. And we get y equals x times e to the x divided by e to the x is x, and then minus e to the x divided by e to the x is minus 1. And we can divide c by e to the x, but that's equivalent to multiplying c by e to the negative x. So we can write the solution for y in that form. Well, for the next example, I'll give you a couple of minutes to work on this one. And then in a couple of minutes, we'll compare notes. So go ahead and integrate this differential equation, or solve it, I should say. What should we do to start with? Yeah, divide every term on both sides by x. So we want it to be in this form. So if we divide every term on both sides by x, and I'm going to replace y prime with dy dx again. So we get dy dx minus 2 over x, y equals x. This is what we get when we divide every term on both sides of this equation by x. Okay, so what's p of x? So this allows us to address a potential issue of confusion. So what should p of x be?
-2 over x.
Yeah, negative 2 over x. So since we're subtracting 2 over x, think of that as adding negative 2 over x. So p of x is negative 2 over x. And our integrating factor is e to the integral of negative 2 over x dx. Okay, so in the exponent, we have the integral of negative 2 over x. We can write that as negative 2 times the integral of 1 over x dx. And the integral of 1 over x dx is the natural log of x. So this becomes negative 2 times the natural log of x. Using properties of logarithms, negative 2 times the natural log of x is the natural log of x to the negative 2. And finally, e to the natural log of something is just whatever that something is. So this is just x to the negative 2. X to the negative 2 is equivalent to 1 over x to the second. So our integrating factor is 1 over x to the second. We're going to multiply every term on both sides of this equation by 1 over x to the second. So when we do that, we get 1 over x to the second times dy dx minus 2 over x to the third times y. And then on the right-hand side, x times 1 over x to the second is 1 over x. And the left-hand side is the result of taking the derivative of a product of two functions of x. So the left-hand side is the derivative with respect to x of the product 1 over x squared times y. And you can always verify that this is correct by applying the product rule to take the derivative of that. So it's implicit differentiation. We're assuming y is a function of x. Okay, now we'll take the integral of both sides of this. The goal, remember, is to solve for y. So when we integrate the derivative of a function with respect to x, we just get the function. So the left-hand side is 1 over x squared y And the right-hand side is the integral of 1 over x dx. And that's the natural log of x plus a constant. So now we just multiply every term on both sides by x squared to solve for y. So y is equal to x squared times the natural log of x plus c times x squared. Okay, the next example. So this time we have t to the second times the derivative of y with respect to t plus 3 times t times y equals the square root of 1 plus t to the second. Okay, so first we want to divide every term on both sides by t to the second. So we'll get the first order linear differential equation in its standard form, dy dt plus 3 over t times y equals the square root of 1 plus t to the second, all divided by t to the second. Okay, find the integrating factor. I'll give you 30 seconds to find the integrating factor. What did you come up with? Okay, let's go through it. The p of t is 3 over t. So the integrating factor is e to the integral of 3 over t dt. And in the exponent, we can write this as 3 times the integral of 1 over t dt. So I'll continue up here. The integral of 1 over t dt is the natural log of t. And in the exponent, 3 times the natural log of t is the natural log of t to the third. So this is e to the natural log of t to the third. And e to the natural log of something is whatever that something is. So in this case, e to the natural log of t to the third is t to the third. Is that what you got? Okay. Okay, that's the integrating factor. So we're going to multiply every term on both sides of this equation by t to the third. So t to the third times dy dt, and then plus t to the third times 3 over t times y is plus 3t to the second y. And on the right-hand side, multiply t to the third times the square root of 1 plus t to the second over t to the second. We're just going to get t times the square root of 1 plus t to the second. The left-hand side is the result of applying the product derivative rule to a product of functions with respect to t. So the left-hand side is the derivative with respect to t of the product t to the third times y. In the step after this one, we're going to integrate t times the square root of 1 plus t to the second. So I'll do a little bit of preparation with the substitution rule in mind. So this can be written as 1/2 times 2t. And then instead of writing the square root of 1 plus t to the second, I'll write it as 1 plus t to the second to the 1/2. Okay, now we'll integrate both sides. The left-hand side is t to the third y. I might as well go ahead and write it out. So the right-hand side is 1/2 times the integral of 1 plus t to the second to the 1/2 times 2t dt. So this is like having u to the 1/2 du in the integrand if u is 1 plus t to the second, right? Are we all okay with that? Okay, so we can, in the next line, t to the third y. When we integrate this, we'll get 1/2 times 2/3 times the quantity 1 plus t to the second to the 3/2 plus a constant. Okay, then we divide every term on both sides by t to the third. We'll simplify here also. 1/2 times 2/3 is 1/3. And so y is equal to depending on how you want to write it, I'll write it as 1/3 times the quantity 1 plus t to the second to the 3/2 plus c, all divided by t to the third. Okay, that's good enough for what we want. Okay, on the next page, we have initial value problems. So here we have x to the second times y prime plus 2x times y equals the natural log of x. With the condition that y of 1 equals 2. So this means that when x is equal to 1, the y coordinate is 2. Okay, take a couple of minutes, see how far you can get in solving this linear differential equation. So about where are you in the process? Somewhere in the middle, I take it. Okay, what did you do first? Divide every term on both sides by x squared. Okay.
And rewrite y prime as dy dx.
Do what?
And rewrite y prime as dy dx.
Yeah. That's my preference. Replace y prime with dy dx. So dy dx plus 2 over xy equals the natural log of x divided by x squared. And then we find the integrating factor. The p of x is 2 over x. So the integrating factor is e to the integral of 2 over x dx. So this can be written as e to the 2 times the integral of 1 over x dx. And so we get e to the 2 times the natural log of x. And 2 times, in the exponent, 2 times the natural log of x is the natural log of x squared. And e to the natural log of x squared is just x squared. Okay, then we multiply every term on both sides of this equation by x squared. So we get x squared times dy dx plus 2xy equals the natural log of x. So notice this is the equation we started with. So sometimes you'll want to watch out for that, because sometimes it will already be set up to integrate. Okay, so the left-hand side is the derivative of a product of two functions. So it's the derivative with respect to x of the product x squared times y. And that's equal to the natural log of x. Then we integrate both sides. So the left-hand side becomes x squared times y. And the right-hand side is the integral of the natural log of x dx. Oh, do you remember the integral of the natural log of x dx? Or just an antiderivative for the natural log of x? Yeah, it's x times the natural log of x minus x. And then we'll put a constant, plus a constant. So I think on the first day of class this semester, we used integration by parts to find this antiderivative for the natural log of x. So use integration by parts. I'll just say parts. Okay, then lastly, we divide every term on both sides by x squared. And we get y equals the natural log of x over x minus 1 over x plus c over x squared. Oh, but we have an initial value, so we should find that. So we want to find c given y of 1 equals 2. So if y of 1 equals 2, that means when x equals 1, y is equal to 2. So we replace y with 2, replace every x with 1, and determine what the value of c is. The natural log of 1 is 0, so we're left with 2 equals negative 1 plus c. And so c is equal to positive 3. Okay, so we can write this. The specific solution is, I'll go ahead and put the natural log of x minus 1 all over x, and then plus 3 over x squared. Okay, the next example. We have the differential equation t to the third times dy dt plus 3t to the second y equals cosine of t, with the initial condition y of pi equals 0. So this time when t is pi, y is 0. So how do you want to start this one? Okay, we can do that. We can divide every term on both sides by t to the third. And when we divide every term on both sides by t to the third, we get dy dt plus 3 over t times y equals cosine of t divided by t to the third. To find the integrating factor, we're going to write e to the integral of 3 over t dt. Okay, this can be written as e to the 3 times the integral of 1 over t dt. This is e to the 3 times the natural log of t. In the exponent, 3 times the natural log of t is the natural log of t to the third. So this is e to the natural log of t to the third. And e to the natural log of t to the third is t to the third. Okay, so now we multiply every term on both sides of this equation by t to the third. And we get t to the third times dy dt and then t to the third times 3 over t is 3t to the second, and then times y. On the right-hand side, when we multiply by t to the third, we're just left with cosine of t. So here's another case where the original equation is in the form that we want it. So after you do this a few times and make that observation, then you'll start to look out for it. Okay, so the left-hand side is the derivative of a product. So if we compute the derivative with respect to t of the product, t to the third times y, and now we can compute the derivative or the antiderivative of both sides. So the left-hand side is t to the third times y, and the right-hand side is sine of t plus a constant. Then divide every term on both sides by t to the third, and we get y equals sine of t over t to the third plus c divided by t to the third. And we want to find c. We're given that y of pi equals 0. So in other words, when t is equal to pi, the y coordinate is 0. So replace y with 0 in this equation, replace y with 0, replace t with pi. Sine of pi is 0, so it has to be the case that c is 0. So our function is just y equals sine of t divided by t to the third. Okay, we have a little over 5 minutes left. And so we'll look at a couple of the word problems from section 9.3. Section 9.3 is the section on separable differential equations. So this problem is number 45 from the textbook. It says a tank contains 1,000 liters of brine with 15 kilograms of dissolved salt. Pure water enters the tank at a rate of 10 liters per minute, and the solution is kept thoroughly mixed and drains from the tank at the same rate. Find the amount of salt in the tank after t minutes. Since we want to find the amount of salt in the tank after t minutes, we'll define a function a of t. The amount of salt, or salt, is measured in kilograms, so a of t will be the number of kilograms of salt in the tank after t minutes. In the second and third sentences, we're given information about the rate of change of the amount of salt in the tank with respect to time measured in minutes. Before going on to the differential equation, just note that the initial amount of salt at time t equals 0 is 15 kilograms. That's what we're starting out with. Okay, well, the rate of change of the amount of salt with respect to time measured in minutes is described in the first, or in the second and third sentences. Okay, so we're told that pure water enters the tank at a rate of 10 liters per minute. Well, pure water doesn't have any salt in it. So the amount of salt entering is 0 kilograms per liter multiplied by 10 liters per minute. But simultaneously, the thoroughly mixed brine departs the tank. Well, the brine that's leaving the tank does have salt in it. Well, at any given time t, the amount of salt is A, and if we divide that by how many gallons are in the tank, so this is A kilograms per 1,000 liters, and it's departing the tank at the rate of 10 liters per minute. Okay, so we'll write the differential equation without the units. So dA dt, this is just 0 and then minus A over 100. Okay, so this is a separable equation. And so we'll write it as dA over A equals negative 1/100 dt. And then when we integrate both sides, we get the natural log of A equals negative 1/100 times t plus a constant. And we're out of time. I'll just do one more step. Solving for A, we get A equals e to the negative 1/100 t plus c. So you can do the rest. Use the initial condition A of 0 equals 15 to determine what that constant c is. Okay, we're out of time. Go ahead and sign in for attendance.
I have a question. Okay, so you're doing the problem and you have this right here, then you go to this. I can't figure out how to get that.
Okay, this is the derivative by applying the product rule to this when you take the derivative. Hang on for a second.
Yep,
I'll
I'm good.
do it on the board here in a minute.
Okay, that'd be good.